I'm Frank. This is Payman. Yes, oh, Canada, indeed. Okay, we're going to talk about maximum likelihood estimation in MAP today. Cool. So last time we did maximum likelihood estimation, we said that there's a likelihood function. It's the probability of the data given the parameters, and we choose the parameters W to maximize the likelihood. And it gives the naive Bayes counting estimates we use, and it's typically easier. Yeah, that's what, and it gives lots of things. We're going to talk about it a bunch today, so don't worry. It's typically easier to equivalently minimize the negative log likelihood, and we're going to do things with that perspective, sort of the optimization perspective on on the objective, just to make everything line up. So here's our maximum likelihood objective. We want to take the argmax of that thing to get our parameter estimate, right? It's equivalent to, you know, sticking a negative sign on there, taking a log and minimizing, okay? Fine. So the log we know is totally fine, and the log turns a product of IID examples into a sum over examples, okay? We use the log likelihood specifically for this reason. It turns multiplication into addition, and generally speaking, because of the structure of Gibbs distributions and these sorts of things, it's going to take things from the exponent and put them down, as you'll see. So if we have some identically distributed, okay, so it doesn't really matter. These are some quantities, obviously. If you have the log of a product of some AIs, then that's the sum of the log of the AIs. And when you have conditionally independently distributed data like this, so DI, you should think of this as an input-output pair for our regression examples, then the probability of the data actually looks like the product over all the data items of the conditional probability of each individual data item given the parameter. So that's the likelihood of example I. And our maximum likelihood estimate is the argmax over W of this product form, but equivalently, we can write that as the minimization of the negative log likelihood when you hit this thing with a log, the product turns into a sum, and you get the sum, the negative sum over all data items of the log likelihood of the data item given the parameter. Okay, fine, cool. So we sort of hand-wavily got to the fact that least squares is maximum likelihood estimation in a model that makes Gaussian assumptions. So let's remember, if I can do this without touching anything wrongly, we have, you know, xi, yi, and we have some data items out here somewhere, and we fit a regression line to those, and we have some residuals, okay? And it should become much more apparent even throughout the lecture today that this epsilon I is the thing that we're talking about, okay? So this epsilon I is the difference, it's the residual, right? Between, yeah, so I mean, just rearrange this epsilon I is, you know, yi minus W transpose xi is the residual. We've been calling this Ri before. And we assume that, so let's assume that the population of these over all of the input-output pairs is distributed conditionally IID, given the model parameters in the input, and that it follows a standard normal distribution, also known as a Gaussian distribution. So this leads to a Gaussian likelihood for each example of the following form. So if you plug in the definition of epsilon I here, then we get, you know, that the conditional probability of the output given the input and the parameter looks like this. Okay, it says a normal distribution centered at 0, where 0 is sort of like here, right? The predicted value. Right? Okay, so if we want to do maximum likelihood or minimize the negative log likelihood in this model, we set up our loss function as being the negative log likelihood summed over all the data items, right? Where the form of this, by assumption, is Gaussian like that, right? So if we plug that in, that's what we get. If we hit this product with a log, we get a log here, a log of a constant, Eventually, we're not going to care about this. This is a constant. So with respect to W, so for optimization purposes, we don't care about this root log 1 over root 2 pi. And we have log and an x here. They're gonna cancel each other, just like we show there. So we're left with this sum over the data items of constant times a term that should be starting to look very, very familiar. The negative here cancels with the negative here. This we're going to ignore, and what we're left with is some constant plus the sum over all items of the residual squared divided by 2. And if we put that into matrix vector or matrix norm form, that's what we saw before. That's the L2 regularized L2 squared loss on the computed via the residuals, right? So that's our standard least squares loss, basically, right? Okay, cool. I suppose I should stop here. Does it make sense to everyone? Are there any questions about this? We're not doing anything new here. We're just saying that, like, look, if you make this distributional assumption about these residuals and you follow through with maximum likelihood estimation, the maximum likelihood estimator, the thing that sets this parameter, right, has the exact same form as the loss function we saw before. That's it. So you can go the other way and say that this loss function can be interpreted as maximum likelihood in a model in which we assume that the residuals are normally distributed. Okay, we'll take that as stunningly clear, so I'll keep going. Great. It's worth pointing out that what we're talking about here are discriminative models, okay? Notice that we maximized a conditional likelihood, so the conditional probability of the output given the input and the parameter, not the joint likelihood, not the joint likelihood of the input and the output simultaneously. So we did maximum likelihood conditioned on the features X, the input being fixed. We're not computing a likelihood of X here at all. When we do modeling like this, it's called discriminative modeling or supervised learning, right? A generative model would optimize actually this. We would learn the joint distribution of X and Y. And then like in naive Bayes, we would use Bayes rule to turn it around, basically. Most of what we talk about in the class are discriminative probabilistic models, least squares, robust regression, logistic regression. And you can use very complicated features because you don't actually model them. Like if you think about the probability distribution over X, which we think about when we do naive Bayes, it's complicated. It's very high dimensional and it's very difficult to estimate and fit well. We do actually look at generative probabilistic models in the course, naive Bayes being the principal one. We'll talk about linear discriminant analysis maybe at some point. But basically, we often need to make very strong assumptions because we explicitly model X, that we learn a probability model of the inputs. And a full reasonable belief is that generative models work better often when you have small n, a relatively small number of data points. Okay, so we're there. We've got that least squares is maximum likelihood under a Gaussian conditional distribution assumption about the residuals. Okay, so if you make this assumption about how the output is distributed and you compute the maximum likelihood estimator for W, you arrive at a loss function that will allow you to get the maximum likelihood estimate of W by minimizing this loss, right? So you get the least squares loss. Okay, if you make a different distributional assumption about the conditional distribution of the target given the input, namely that it's Laplace distributed, so this is a different distribution, this is a Laplace distribution rather than a Gaussian distribution, right? And you go through the same procedure of taking derivatives and log likelihoods and summing over the data points and that sort of thing, you get that the maximum likelihood estimator is the minimum, or the maximum likelihood estimate is the minimum of this loss, which, Payman, is the
L1.
It's the L1 loss, but it corresponds to what kind of regression?
Kind of regression.
Let the kids beat you.
Remember.
Okay, taking from the audience, robust, there we go, robust regression. Oh man, I just write here, TA fail. I'll get rid of that, okay. Anyway, so yeah, it's robust regression, right? And the point is that other likelihoods lead to different errors and losses, okay? Sigmoid gives rise to the logistic loss, okay? We'll talk about this, right? So why does this distributional assumption give rise to what we discussed as a robust regression loss before? Like, what's the interplay between the two of them? Well, if you plot out the probability density functions for a normal distributed quantity and a Laplace distributed quantity, and you pay attention to what happens in the tails, in particular, you pay attention to what really happens in the tails. The Gaussian goes to 0 really, really fast, and there's always a little extra mass out here, okay? And what this means is that when you're fitting a regression model, and you have and you're making some distributional assumption about the distribution of the target given the input and the parameter, right? If you make a distributional assumption that's heavy-tailed, this being, that was totally supposed to be centered on the that was really bad. Oh no, they don't do the full length erase. Okay, fine. If you make a heavy tail distributional assumption, then there's some probability mass that allows outliers out here. Okay, so the Gaussian has light tails, which means basically it forces everything to be close to the mean. You have to be close to the mean, otherwise so basically your parameter estimates have to be close, have to result in a regression line that's close in the squared sense everywhere. Laplace has heavy tails, which means that actually, in terms of the probability that you assign, like having an outlier isn't such a big deal. It actually has a relatively high probability under your distributional assumption about the error that you make. Okay, cool. Yeah, cool. Yeah, tail means mass of the distribution far away from the mean. The student t is even more heavy-tailed. So if you plot a student t, it's going to be even more heavy-tailed. So in other words, there's going to be a gap even over the Laplace distribution, so you can make more and more robust regressors. But in this case, the negative log likelihood is non-convex, and so the optimization problem gets harder. Okay, how about this funny business where we took our linear model and turned it into a probability for classification purposes, right? So we got probabilities from binary linear models with a sigmoid function. So we have W transpose X. This is our linear model that is equal to Zi, right? This gives us a number in the real line. And we said if we want to turn this into a probability, we pass it through the sigmoid function here, H. It has this functional form and looks like this in terms of a plot. We went through this, right? So maps a real line to 0, 1. Cool. Okay, there we go. So if we do maximum likelihood in this model, and I'll explain what I mean by this model in just a second, right? Basically, the model is P of yi equals 1 given W and Zi is, W and Xi is H of Z, okay? Cool. So if we do maximum likelihood in this model, that gives us a logistic loss. So let's look at this just a little bit more. So so again, P of yi equals +1, and Zi, remember, is W transpose Xi. So we're conditioning, it's a conditional distribution condition on the parameter and the input, right? If we define the probability of P y being 1 to be the sigmoid function applied to our linear model output Zi, then first we can write that the probability that yi is -1, given zi, is just 1 minus that, right? I mean, we're doing binary classification, so fine, that's a probabilistic statement. We can, plug in the definition we just made for what the probability that the class label is 1 in here, and with a little bit of algebra on the sigmoid function, you can show that minus the sigmoid function of a value is equal to, 1 minus the, you can basically demonstrate this. We're not going to do it. It's annoying algebra, but it's not so hard. Okay. That means that if we have binary classification, we do this +1 -1 label trick for, spam, not spam, or whatever, then we can just write both cases, P of yi, no matter what the value is, right, given z, is equal to h, the sigmoid function applied to y, times z for that data item, right? So cool. So we convert from this real valued quantity, W transpose xi, into a probability of y using this rule. Okay, cool. H is the sigmoid function, so we can just plug this in, right? And maximum likelihood with this particular likelihood is equivalent to minimizing the logistic loss. Okay, so negative log likelihood for our regression model is all the data, right? We make the IID assumption here. The log that turns the product into a sum again. So we have the log likelihood of an individual data. We wrote down what the form of this term was right here. So we have, this is basically the logistic function applied to our linear model. If we plug in the sigmoid function, the negative log likelihood is the logistic loss, right? So the negative log likelihood of W is the sum over all the data items, the sum of the log of this logistic function here. So we're just taking, this is just log likelihood for every individual data item, right? And if you apply the log here, we have log of 1, which is 0, minus log of 1 plus x, and the two minus signs cancel. So we just have exactly the logistic loss that we were looking at before. Okay. So the assumption is that the conditional probability of a class label being +1 or -1 given xi and w is this or this, either one, right? There's a link function from a linear model. The link function is a sigmoid function. When you take this point of view and you do maximum likelihood, you get exactly the logistic loss we were looking at before. Okay, make sense? All right, cool. So we just derived the logistic loss from the perspective of maximum likelihood estimation, right? That's cool, right? So instead of this kind of weird way we got to it where we said, okay, well, we have the 0-1 loss and we're going to do all sorts of things, and then we got to, the log sum x trick to smooth the 0-1 loss, right? We now have the logistic regression is doing maximum likelihood estimation in a probabilistic model, right? So the training and prediction would be the exact same as before. We still minimize the logistic loss in terms of W, but this perspective, this probabilistic perspective, justifies the use of the sigmoid for that we put forward sort of hackily before, where we said the probability that an email is important is like this. Well, actually, that's the distributional assumption that we're making, right? So they kind of go hand in hand, right? So we derived all this stuff from some like, ooh, this makes sense perspective. What's really going on is we have these likelihood functions and we're operating in maximum likelihood land. Okay. We could do the same thing for multi-class logistic regression. We talked about multi-class classification, where we wanted the linear model output for the true class label yi to be the most positive amongst k real numbers, where c is in 1 to k, right? So if you have k real numbers, which are the outputs of the linear models, each of the linear models, right? We want to map those probabilities for use in a discrete conditional probability distribution, right? A very reasonable thing to do is use the softmax function. So you can think about the probability that y equals 1 is exp, Z1 over the sum of everything, and then exp of Z2 over the sum of everything, and so on and so forth out to some vector. And now we have a categorical distribution over 1 to k, this 1 to k, with probabilities that are given by the exponentiated output of our linear models divided by basically normalized, right? So, so the point is we have some real valued quantity that our models are outputting. We want to make it non-negative. A natural thing to do is to exponentiate it in order to do that. You don't have to use the exponential function, but it's a natural thing to do. And then the denominator actually just sums to build a categorical distribution over the class identity, okay? It gives us a probability for each of the k values of C. And if you go through the maths again and compute the, and do, write down the negative log likelihood, and do a little bit of algebra, what you arrive at is the softmax loss. Okay. Questions at this point? Either everybody's thinking about the homework, everybody's wishing they were outside in the sun, or I'm being clear, or everybody's looking at Payman's face, who's clearly struggling to stay awake right now. So.
No, you're doing a good job.
Okay, or I'm just like being amazingly clear today, and everybody's just like totally happy with the work product. Sure, that's the case. The good thing about this is you can take your device outside. Just go outside, listen to the lecture, put it in front of your face and walk around. It's like a different interpretation for a lot of old material. Yeah. So yeah, I think that's a very very reasonable thing to think. So we're going to go a little bit further in this direction even. So in this abstract setting that we're talking about, the data D, whatever it is, all of the pairs of input-output examples or something like that, when we write down the maximum likelihood estimate, it's it's what we have here. We have the likelihood function, and we're trying to find the parameter that maximizes the likelihood. But actually, the other section has been thinking more about this than you all have, at least explicitly in terms of the comments. Conceptually, the maximum likelihood is kind of a weird thing, which is that we're trying to find the W that makes the D have the data have the highest probability given W. And Ramon asked a really not boring question, which is how does knowing these correspondences help do stuff? It's entirely a totally legitimate question and a very good one. And I'll actually address that in a couple of points later on in the lecture, and we'll talk about it after the lecture. But the long and short of it is it's a way of organizing your thoughts that's a little bit different. And it means that it will be easier to build different loss functions that correspond to different kinds of data and these sorts of things, because you can always build generative models or conditional generative models of different kinds of data. Another thing that I sort of forgot to mention, but it should be relatively obvious at this point, is that we've just put regression and classification on exactly the same footing. They're not different at all. They're exactly the same thing. And I've said that a couple of times during the course, right? All that's different is the link function and the likelihood function at the end. You have some sort of model, conditional model, and then a link function to some probability distribution of the thing of your label given your data. So even that as a general principle actually helps you think about what regression and classification are. They're kind of the same, right? But maximum likelihood by itself is a weird deal because we're kind of thinking the wrong way. And maximum likelihood by itself tends to lead, leads to overfitting. Notice we've just derived the standard loss functions, but there's no regularization on any of the things that we've talked about, right? Any of the loss functions we just talked about. So the data could be very likely for some very unlikely W, right? So, like all the stuff we talked about when we were pre-regularization, a complex model can overfit by memorizing the data. What we really want is the W that has the highest probability given the data. Okay, and that's sometimes weird for people, particularly when we come at it this way. But we talked about it a little bit after class last time in this section. I think people sort of got it there. So maximum a posteriori estimation, or MAP estimation, maximizes the reverse probability, the probability of the parameter given the data. That's actually what we want. It's a probability of the of the parameter taking a particular value given the data, right? And maximum likelihood and MAP are connected via Bayes' rule. So the posterior probability of the parameter vector given the data is related to the likelihood of the data given the parameter times the prior belief that you have about what the parameter value is over what we call the evidence, or the probability, the marginal probability of the data. And since in this course we're not going to talk about integration, we're not going to do full Bayes at all, we're going to be just messing around with W and trying to learn W as a point estimate. You can sort of leave off this bottom term because it doesn't have anything to do with W. And now we're left with the likelihood, the prior, and the posterior. So MAP maximizes the likelihood, that's good, times the prior, and this prior is some belief about what we think the model parameters should be, okay, before we look at the data. And the prior, basically what you'll see is, it can be used in lots of different ways, but in what we've covered, it's going to basically show up as regularization and help the model not overfit. So from Bayes' rule, the MAP estimate with IID examples, it looks like so. We know that the posterior is proportional to the likelihood, and we know the likelihood decomposes into the conditional probability, independent conditional probability of each data item given the parameter times the prior. If we take the negative logarithm again and seek to minimize this, what we get is, the sum over our data items of the individual data item log likelihoods, and a negative log prior. And in our developed shared vocabulary, this thing is going to be the loss that we've been talking about, and this is going to be the regularizers that we've been talking about.
Is there some smart machine learning way to choose parameters for the prior?
Oh, yeah. Oh, yes. Okay. Yes, there. Yes, there is, and it's not pretty in general. So learning the parameters for the prior is called type 2 maximum likelihood, and it involves actually integrating over the parameters, and that requires talking about full Bayesian treatments in order to actually really talk about that, which we don't do in this class. That's a 540 or 440 or that kind of material. Okay, but it's a very good thing to keep in mind. Yeah. So we can view the negative log likelihood as a regularizer, and many regularizers, just like our many loss functions, show up as correspond to distributional assumptions, conditional distribution assumptions, i.e. likelihoods. Many regularizers are equivalent to negative log priors. So let's do an example here. So let's make an assumption. Let's assume that every dimension of our feature, of our parameter, W, comes from a Gaussian with mean 0 and variance 1 over lambda, okay? So this is our prior belief about what the parameter vector should be. And by the way, let me just put this out there right away, up front. We made several kind of ham-handed attempts to suggest that small parameter values are good, right? They lead to good generalization performance. And in the polynomial perspective, you can sort of think of like L1 in particular as limiting the number of terms, which means it limits the complexity of the model, which means that like we want a small number of relatively large parameters and a whole lot of zeros. So we want the parameter vector to be in general small, right? So if we make this IID assumption about the dimensions of the parameter vector, we say, okay, we just take a product over all the dimensions of the probability of the individual item. We make a Gaussian assumption we just did here, which is 0 mean. So there's no minus mu squared here. It's just WJ squared, and then we divide by 1 over lambda. So that comes up in the numerator. So this is the Gaussian assumption for each individual dimension of the parameter space. We know that when you multiply a bunch of exponentials together, you can move products here into sums here, right? And now if we take a negative log prior where we define the prior to look like this. The log is going to kill the exponent here. The negative is going to kill the negative here. And what we're left with is a regularizer that looks a heck of a lot like the 2 norm squared regularizer that we looked at, or L2 regularization, okay? Because that's what it is. So actually, right, you're making an explicit assumption about what your belief is in the parameter values when you impose a regularization term like this. You are saying that you believe a priori that the parameters of your model come from or should be close to 0, and you'll be surprised in some distributional form where the variance is 1 over lambda. Okay, cool. So with this prior map estimation with IID training examples, looks like this. So we have our argmin of negative log likelihood terms minus the log prior. Well, we already dealt with this. That's the what we had before, but now we have our regularization term, right? So it's exactly the loss plus regularizer when we did L2 regularized least squares. Okay, cool. So this is exactly the same slide. I forgot to take it out, sorry. Actually, I know that it's okay, not the same slide, but I know that slide is repeated. Sorry about that. So map estimation gives a link between probability loss function, right? So if you have a Gaussian likelihood plus a Gaussian prior gives us L2 regularized least squares. That's just what we did. So we made a distributional assumption about the output given the input and the parameters, and we made a distributional assumption about the parameters. And then map estimation is equivalent to minimizing this loss function. So they're kind of they're equivalent. This whole thing and that, right? The fun thing is now if we make distributional assumption changes about various parts, about the likelihood or the prior, we get different things. So if we make it the Laplace distributional assumption about the output given the input, right, and we make a Gaussian assumption about the distribution of the parameters, then map estimation is equivalent to minimizing the loss function that looks like this, and that is robust regularized regression, right? Cool. Of course, it should be relatively clear, if it isn't already, that like this thing is an n-dimensional vector and this thing is a d-dimensional vector. So as n goes to infinity, this vector is going to get super, super long, and it's going to dominate basically the loss function. Another way of looking at it is, if you have some distributional assumption, I don't know how far back I have to go. Yeah, if you have a whole lot of data points, this thing eventually is going to come to dominate the regularization. Like this is going to basically go to 0, relatively speaking. So basically, as n goes to infinity, the effect of the prior regularizer goes to 0. By the way, there's a beautiful theorem in statistics called the Bernstein-von Mises theorem, which is basically a statement of this for parametric models. That's just absolutely beautiful. So you should also be aware that there's an invariance to parameterization thing going on here. So unlike with the maximum likelihood estimation, the choice of your likelihood variance changes the map solution. It's a detail, you don't have to worry too much about it, but you should be aware of it. This is the repeated slide. I apologize for that. I shouldn't have gone to the beach. I should have taken it out. So many of the loss functions and regularizers we have probabilistic interpretations. Laplace likelihood leads to absolute error. Laplace prior leads to L1 regularization. The choice of likelihood corresponds to choice of loss. Our assumptions about how the yi value is basically, the likelihood is really our assumptions about how the yi values, the outputs, are generated from the inputs and the w's. Could we just use a non-constant lambda if we don't want to lose the effect of regularization? Oh, that's dangerous. generally people appeal or want to appeal to these asymptotic results so that you know, for instance, that the map goes to the maximum likelihood solution because the maximum likelihood estimator has some nice properties. So I would warn you away from that idea unless you have very strong belief in your in your model. In which case, if you have belief that scales within or something like that, then really effectively you say that your model is, you don't need any data, right? And that's a maybe you know that, but in our case, in the general case, we're not gonna know the model, so that's a little dangerous to do. Yeah, so the choice of prior corresponds to the choice of regularizer, and yeah, it's our assumptions about which values of W are plausible or desirable or whatever. We can regularize lots of other models, right, via this framework. So something to work out on your own if you haven't done it. Like we did this, we did this funny problem doing maximum likelihood estimation in the naive Bayes case. In particular, we had this counting estimator problem where if you had a 0 count in the numerator, you were kind of screwed. Obviously, you had a 0 count down here, you're screwed too. But in particular, you know, like we had a problem. Like if the count was 0, our classifier was goofy. So we did this add 1 magic thing from thin air, basically. But if you think about what's going on there and you write it down, basically what we're saying is that you know, the data here is Bernoulli distributed, and the prior that we would use on the parameter is a beta prior. And if you do Bernoulli beta and you do maximum a posteriori solution, maximum a posteriori estimation, then these counts just pop out. They arise directly from using a beta 1 prior. So Laplace smoothing just comes from regularization in the form of adding a beta prior to our Bernoulli likelihood. Okay, I think we should soldier on, but I'll take a question or two here if we have them. What's a beta distribution? It's P of theta given alpha beta, something like theta to the 1 minus alpha, and then 1 minus theta to the 1 minus beta, and then some normalization constant here, something like that. It's a distribution over probabilities. Beta 1 is indeed uniform, yeah. But that's entirely the point. So if you have a Bernoulli likelihood and you have no terms, what you want is you want to smooth towards a uniform distribution, and that's where it happens. Normalization constant, which is literally what Frank wrote. Yeah, exactly. Yeah, but I don't want to have to think about what the functional form of that is. Yeah. And just for the fun of it, since you know you all are having fun, the reason why I can at least remember the functional form, this part of the functional form for the beta distribution, is that I know that if I have some data item y that has parameter this, which is y, indicator function y equals 1 and 1 minus theta indicator function y equals -1, spam or not spam, something like that. If I want to construct the posterior distribution of theta given alpha, beta, and y, then if you look really carefully, when you multiply these together, you have these terms which are theta to something, and these terms which are 1 minus theta to something. So the functional form of the posterior distribution is actually beta distributed. And when you do this, you get a count of the number of positive y's, a count of the number of negative y's, and some plus ones here, basically, or some alpha beta here. Okay, and that these alpha betas are the generalization of the smoothing that we did, called Laplace smoothing. Anyway. Why do we care about maximum likelihood in map? This is a question that basically came up on the chat channel, right? It's a unified way of thinking about many of our tricks. We get a probabilistic interpretation of logistic loss, means that, you know, classification and regression are basically the same thing. Laplace smoothing and L2 regularization, they're doing the same thing. They're just different distributional assumptions about the parameters. And there, you know, this map thing is related to a couple of different ways of reducing overfitting in complicated models, averaging and regularization. Unfortunately, these are this requires fully Bayesian thinking, where you average over the models weighted by their posterior probability. This does allow you to use really, really complicated models and not have to worry about overfitting at all, which is cool. And that's, you know, what's in 540, 440, and my course 532M or whatever it is. I have no idea. But if you're interested, you should come join us. We'll talk about these things. It also helps us think about, you know, different kinds of losses, and like being able to write down losses for more complex kinds of regression or classification problems. So Inali map gives us losses for classification with basic labels, least squares for regression, absolute loss for regression, logistic regression for binary labels, softmax regression for multi-class. But you can build likelihood functions, and likelihood functions exist for different kinds of discrete labels and different kinds of continuous labels. So if you have ordinal data, you can build explicit probability models for ordinal data. Count data, if you have count data that you'd like to regress to, then you can, for instance, use a Poisson likelihood, and now everything that you've learned automatically applies. You can automatically apply, you can derive the loss functions, you can do maximum likelihood, you can do you know, maximum a posteriori survival data. If you have centered data, you can use centered likelihoods. You have unbalanced classes. That thinking this way helps you a lot in figuring out how to deal with that. Basically, you define the likelihood of the labels or the outputs, and you use the negative log likelihood as a loss function. So now you can, we've expanded your arsenal quite a lot, even if it's not obvious right now. And you can also use ratios of probabilities to define more losses. You can define the losses from binary SVMs and multi-class SVMs as basically ratios of probabilities, and you can see about that in the lecture slides and in the bonus slides, if you want. But we've made it somewhere. Yay! We should all be happy as it gets dark and we descend into Vancouver November seasonal depression. Okay. In part 3, we've talked about linear models. We predict based on linear combinations of features. We talked a lot about changing bases. We can replace a d-dimensional feature with a k-dimensional z, and basically use a linear model there. And we talked about polynomial bases, and we talked about the very powerful radial basis function, non-parametric bases. And we, you know, like we've established that regression is supervised learning with continuous labels, and we talked a lot about the squared error and showed that we could solve or do parameter estimation in such a model by solving a system of linear equations. We talked about gradient descent, which allows us to find local optimum of smooth losses or objectives. If your loss happens to be convex, you can get to a global optima efficiently, usually. We know to smooth a bunch of our losses using Huber or log sum x tricks, that sort of thing. And we know how to deal with really, really large data sets, even with very large feature spaces using stochastic gradient. Although we talked a little bit about step size. Kernel methods allow us to compute using similarities between examples instead of features. And that's really, really critical because it allows us to think about, basically pretend and actually compute in very, very large, even infinite dimensional feature spaces. We we waggled our way through feature selection, which is messy and unpleasant to deal with. We talked about forward selection, and then we talked about L1 regularization, which simultaneously regularizes and selects features. And we just established basically the Laplace prior that does the same thing. So there's a probabilistic interpretation for that. We introduced regularization, where we can control model complexity by introducing regularization terms. The squared error is not always what we want, right? Absolute errors gives rise to robust regression, and different losses are better for different kinds of data. Logistic loss and hinge loss for binary, and softmax for multi-class. Then we just went through the maximum likelihood map perspective, where we can look at the losses and interpret them as log likelihoods and regularizers as log priors. And this allows us to define losses based on probabilities. So the story so far, we did supervised learning on counting and distances. We did using models based on counting and distances. We did unsupervised learning based on counting and distances. We did just now finished supervised learning based on linear models and gradient descent. And now, next lecture, we're going to do unsupervised learning using linear models and gradient descent. And that's pretty much it. Maximum likelihood today, map, gives us a probabilistic interpretation for regularization in addition to maximum likelihood, which is, a way of thinking about loss in a different mathematical framework. And really what this framework gives us the ability to do is think about losses for weird scenarios that are where our data is in a different space, basically. Cool. Awesome. What is unsupervised learning? Cool. What is unsupervised learning? That's unsupervised learning. If you want to learn not a conditional distribution, but a joint distribution, that's unsupervised learning. So there's no classification, there's no label, there's no output, there's no whatever. You're just learning patterns in the data. Another way of thinking about it, which is not unreasonable in the context of this course, is to think about some sort of way of extracting general purpose features before you ever get to your supervised learning task. So here's a bunch of images. Please go extract decent features, some representation of those that will be useful in general. I'm just curious. Clustering is a bit like unsupervised learning. Yeah, indeed. I'm just curious, can you use maximum likelihood estimation to estimate model prediction uncertainty? How confident is the prediction of the model? So this is a really, really good point to think about, Matthew, and you're really close to like getting it, right? There's two sources of errors, okay, and we have to be really careful about that, right? So one source of error is like we're making an assumption about how far off our predictions are. But let's be very careful. What we're saying is when we do map estimation and we use a point estimate, what we're saying is we're preferring a particular parameter value, and we've assumed to get there the distribution of the errors. Okay. So if we want to estimate model prediction uncertainty under our assumptions, right, we actually have to consider not a point estimate of this, but actually the posterior distribution of models, which may be a distribution over regression functions like this, which means that your prediction, the actual uncertainty about your prediction, is much, much larger than the likelihood assumption that you made. So the a posterior predictive, I guess another way of putting it is this this is not in 340, so, but let me just say it anyway. If you have your training data, which looks like this, and you have a test data point, y, yeah, so you need, let's do it again. If you want P of y test given x test, okay, this is best approximated by P of y test given so there's got to be a W in here. There's yeah. So x test W, P of W given x and y, and you integrate this thing over dW. Okay, so this thing shows up here. We've been talking about point estimates, but what if you really want to do posterior predictive inference, then you have to actually integrate over the full posterior, and that gives you your actual uncertainty. This should have x and y in it as well. That gives you your actual uncertainty about the prediction that you're making, taking into account all of your stuff. A little question from previous lecture: won't hinge loss penalize too much for predicting too correct, or is it just relatively better than squared error? Shuyan, this is a good question. So. So the hinge loss won't penalize for being correct at all, right? So when you're correct, there's no penalty. It will penalize linearly when you're too incorrect, and that is arguably better than that squared loss. But the real issue is that, like, over here, this is bad. Right? You don't want to penalize. You don't want to penalize for being too right. So it's kind of the other way around. But isn't that intractable since you never really get the distribution of the weights? It's, as it turns out, actually in linear regression, this thing is tractable, and the posterior distribution of the weights in a regularized linear regression model is Gaussian. So there's a closed form solution for that. It's not that easy to get to, but it's tractable. For most other models, it's totally intractable because of the integration that you need to do. But there are lots and lots of ways of getting around that intractability. We spend a lot of time working on them. That's arguably what I do for my day job.
I think by predicting too correct, what Shreyan was meaning was that, WX is like very too positive. So, and also the labels are also should be +1, right? So when it falls on the right side of your graph over there.
We'd have to go back to it. I'm going to get the mins and the zeros and the pluses, but none of the hinge losses or any of those penalize for being too right. Period. There's no penalty for being too right. Ever. And Ming, don't say things like that. That's not true. All right. If you got lost on some of this, that's what, office hours, TAs, tutorial, that sort of thing, that you'll get there. It's, you know, quite often there's a pretty good chunk of the class that's seen these sorts of things before. And don't be discouraged by the fact that some people, some people have seen it before and ask questions that are a little bit beyond where we are. But you know, you got to see it the first time. Everybody's got to see it the first time sometime, and it's tough the first time you see it. When I saw this stuff the first time, I was like, "What in God's name is going on?" And it took years of practice in order to actually really, really understand what's going on. Probably more time than most of you will need. My impression of the people that take this class is that in general, y'all are pretty darn smart. So it's just effort and practice. Definitely don't give up. Keep going, right? Yeah. You'll get there. If I got there, you can get there. That's for sure. All right. I think that's good. Thanks, Payman.
Thank you. Nice weekend.
I agree, Ramon. Yeah. Thank you. Cheers.